Now, according to the last video we made, now this lecture we are going to continue the repertoire method. Now we are going to solve a more complex set of expressions. That what we have here, this is what we have last class. I promise that this class we're going to solve this one because this one is more complex than that. So just by observation, you can say that this one cannot be simply represented by n power 0, n power 1, n power 1, blah, 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 because this here, there is 3 power n. That is what is more than the first one. So the method is not changed, still use repertoire method. Now we use the generalized form. We need to write this into T1 equals to A1, Tn equals to Tn minus 1 plus An for each n bigger than 2. So now we have to separate it into 2 parts. You see that there is power part and there is the normal part. So we separate the normal part. We found that the highest power is power 1. So we have to check from power 0, power 1 to power 2. And for the 3 power n, you see that in high school we have learned that you see this polynomial and the summation is similar as this one. So here we get 2 power n. So use the same sort, we can still use Sn to get 3 power n. So how to represent this? First start from most simple part. The first 3 steps are to find this. We want to find this n. So start from 1, a1 equals to 1, an equals to 0 for n bigger than 1. For n2 equals to n1 and n equals to 1. For n3, n squared and dot dot dot, an equals to 2n minus 1. For the fourth step, we have to check how we can get 3 power n. Just simply we can write 3 power n directly because there is no other coefficient in front of this, so you can represent that 3n directly here. So a1 equals to 3, an equals to 2 multiply 3 power n minus 1. So that is simply we just need to write it here. There's no other something like more complex than this one. So Sn4 we get this is 3 power n. And so now we get Sn, Sn1, Sn2, and for Sn4. So Sn we have 1 and 3 power n, and we need to use linear combination of these 4 to get Sn. So how we linear combination? Still use the same method used in last class. We use this symbol to represent, that is a1 and that is an for this n bigger than 2. And for alpha, beta, gamma, and this theta, we first need to solve. We can first need to observe that which power is unique. By finding the unique power, we can first get the solution of the very simple and easiest variable. So we see that there is only one element that is in the shape of 2 power n. So this is the only element that can give 3 power something. So you need this theta needs to be 3 over 2, so that when multiplied by 3 over 2, this can be like 2 multiply n minus 1 plus multiply 3 over 2 equals to, you see, this cancel out. And here it gives 3 power n. So it deals that theta is equals to 3 over 2. And for 3 over 2, we now have 3 power n. And what we need to solve is this one minus 3 power n. So we need to find the linear combination for n. And so you see that the only elements that left, because this we have deal with, so we don't need to consider this one. Just throw them away. We don't need to consider these 3. 1, 2, 3. And you see that gamma is the only element that gives n. So gamma equals to 1 over 2. That gives n minus 1 over 2. So what is left is we need to find 1 over 2. You see that beta is only element that give 1 over 2 down here, not to mention this part. We just first want to find this part, just the part down here. So beta equals to 1 over 2. So by now we have solved all the linear combination for these parts. So what about the upper parts? How we need to solve the upper parts? You see that the upper parts, there is 1. So what is left is that 1 equals to alpha plus 1 multiply beta, 1 multiply gamma, 1 multiply, that is 3 multiply theta, that is 9 over 2. So we saw that alpha equals to minus 9 over 2. So by linear combination that we can check that Sn equals to alpha Sn1 beta Sn2 gamma Sn3 plus theta Sn4. So now we give this one. You see that it satisfies, and you can check that even if for n equals to 1, the condition also holds Sn equals to 1. So there's no difference between n equals to 1 or n bigger than 2. So this satisfies for all n bigger than 1. So this gives the representation of S1. So you see that now here's how powerful the repertoire method is. Given that a very complex representation of or function of polynomials, it can still be represented as long as it can be separated into those linear combination parts. So that's all for today's lecture and application or simple application for repertoire method.